Okay, we are in chapter 8 still. This is section 8-2, and this is recording number 4. Okay, we're at the end of section 8-2, and we're going to talk about this other method here called the p-value method. Now, let's get some context on this. Okay. Okay, back here in the introduction, approximately page 414, he discussed how there's different methods of doing this. The traditional method, the p-value method, and what's called the confidence interval method. So what we've been talking about so far has been the traditional method. Now we're going to spend a little bit of time talking about the p-value method. Well, since we're in section 8-2, we are talking about testing for means and with a condition that you know the sigma of the population. But it's the traditional method that we've been talking about up until now. Now we're going to talk about the p-value method. Okay, so it's the p-value method, but we're still in section 8-2. So we are in this scenario where we know the sigma. Okay, so what's the p-value method? The p-value method comes up a lot nowadays because it's in the statistics packages, okay? A lot of times they will give you the p-value. You'll see this in research papers and so forth. The p-value, also known as the probability value, is the probability of getting whatever you got, the sample statistic, whatever you got, the probability of getting that particular X bar as an example. So it's the probability of getting the particular X bar that you got, that particular sample mean, or an even more extreme sample statistic, okay? Maybe you're talking about the probability of getting this one right here, the X bar, the one we just did with the stroke victims and the costs, okay? The X bar was 26,343. So that's the 26,343. What's the probability of getting that exact number or even more extreme? 26,343 corresponds to a z-value of 3.04. What's the chance of getting that number or even more out to the extreme? I'm sorry, I was off the screen there. So 26,343 corresponds to a z-value of 3.04. What's the probability of getting that or more? That's this area under the curve right here. Okay, so that's what he's talking about here. Probability of getting a particular sample statistic or an even more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. So just like before, we kind of, the null hypothesis is the status quo. That's what we assume to be true. We're not going to change it unless we're convinced, okay? And the null hypothesis is what we assume to be true. The alternative hypothesis is what some researcher is trying to convince us is true. So in other words, the p-value is the actual area under the standard normal distribution curve or any other curve. It could be the chi-squared curve or the t-curve, whatever. It depends upon which statistical test is being used. And it represents the probability of a particular sample statistic, like the X bar, the value for that X bar, or an even more extreme sample statistic occurring. So that test value, what's the chance of getting that particular test value or more? So here's an example. Alternative hypothesis is that mu is greater than 50. We have a mean of an X bar is 52. So here's my 52 right there. Boom, here's my 52. Okay, and here's my mu. Boy, this is awfully hard to get it all on one screen. I'll tell you that, folks. Let me pause. Okay, what I had to do is to get everything on the page here, I had to expand the field of view of this program I'm using, and that makes it a little bit smaller. So I'm sorry about that. But on the other hand, you should be using your book here, so you should be able to follow along, I think, without any problems. Okay, so here's the example we're going to use. We have a null hypothesis that is 50. Okay, that's what we assume to be true. H1, that's the alternative hypothesis, also known as a research hypothesis, we're saying that mu is greater than 50. The mean of some sample that we pick is 52. So here it is. Here's 52. Here's 52. Where is it? It's to the right of the critical value for alpha equals 0.05. So let's say the computer printed a p-value of 0.0356. This is all from a computer, not something that you would calculate. The probability of getting a sample mean of 52 or greater, in other words, going in this direction, is 0.0356. So the probability of getting a 52 is, or more, is right here all the way to the right. That's the area 0.0356. Okay. Now let's suppose the alpha was 0.05. Well, 0.05, that would be this critical value. So to the right of this critical value is 0.05, that's 5%. Now suppose the alpha was 0.01, 1%. So that would be from this point to the right. So these are all areas under the curve. The areas under the curve represent the probability. Okay. So in a situation like this, the computer kicks out 0.0356. So what you say to yourself is, okay, it could have happened by mistake, or by random chance, excuse me. It could have happened by random chance that the X bar is 52 when the mean of the population is 50. Okay, it could have happened. However, the chances of me getting that number, of me getting a 52 or more, is 0.0356. That's the probability. So it's 3.5% that I'm going to get this or more. So then you look at it and you say, well, what are the chances of that happening? I mean, for crying out loud, the chance of getting 3.5% is very low. I'm going to reject the null hypothesis. Or you might say, well, you know what? I don't feel comfortable doing that. There's a 5% chance that I will be less than this number. And you know what? I'm talking about people's lives here. If this medication should be approved by the Federal Drug Administration or not, maybe Food and Drug Administration, maybe I shouldn't reject the null hypothesis. So it all depends upon what the context is. But that's what's going on here is the p-value tells you the probability of getting that particular value or more, and that's the area under the curve. So there's the area under the curve. Okay. All right, so let's see if we can do an example. Same idea with a two-tailed test. If you have a two-tailed test, the area in one tail must be doubled. Okay, so if alpha is 0.05 and the area in one tail is 0.0356, the p-value will be twice that, will be 0.0712. So we shouldn't reject the null hypothesis unless 0.0712 is greater than 0.05. Okay, so let's do an example here. He's got the decision rule here. It's hard to memorize those decision rules. Okay, so we're going to do the hypothesis testing using the p-value, same as before, basically, or to a certain extent anyway. You state the hypotheses, you compute the test value. Okay, you don't need a critical value. You compute the test value. You compute the test value. You find the p-value that relates to that, and you make the decision. Okay, so let's take a look. Cost of college tuition. I want to test the claim that the average cost of tuition is greater than $5,700. You get a sample 36, or your n is 36. The mean, the X bar, is 5,970. Well, it's certainly bigger than, that is bigger than that. Okay. You have a standard deviation of 659. Is there enough evidence to support the claim that alpha is equal to 0.05? Use the p-value method. So I don't need the critical value. I just need to know what the p-value is, and I'm going to use this alpha equals 0.05 to help me make the decision. So here's the hypothesis. The null hypothesis is the status quo is $5,700. The research hypothesis is that it's more than $5,700. I do have to calculate the test value. I get that. Now I got to find this p-value. Now if I have it on a computer, it'll do it for me, but I can do it with my table. I go to my tables. I find the corresponding area under the normal distribution for z is equal to 2.28. It is 0.987. Okay, so that's the area to the left of 2.28. I want the area to the right of 0.987. So that area is, 100% take away the 98.87%, or you can think about it as 1.000 take away 0.9887. You get 0.0113. So what that's telling me is to the right of 5950, that area right here is 0.0113. So what is that telling me? That this is a probability area here. So the probability of getting 5950, the probability of getting 5,950 is, or more, 5,950 or more is 0.0113. So it's like 1% and some change. Well, if my alpha, if my budget for my error is 5%, well, I'm good, right? I can go ahead, I can reject the null hypothesis, because the chances of getting that by random chance is significantly less than the alpha that I'm allowed, that the error budget that I'm allowed. So there is enough evidence to support the claim that the fees are greater than 5,700. Now, here's the kicker, though. This is what makes you crazy. Okay. Suppose he had chosen, the researcher had chosen alpha is equal to 0.01. So 0.01 would be right here to the left, a little tiny, oh, I'm sorry, to the right here, just a little tiny bit. It'd be right here. And what he was saying is, I only want to be wrong 1% of the time. Well, you're wrong 1% and some change. You're wrong, if you reject the null hypothesis, you're wrong 1.13% of the time. I don't want to be wrong that amount of the time. I want to be wrong only 1% of the time. Okay, so kind of complicated. Boy, this just shows you why you got to draw those cartoons, right? Let me squeeze in one more example here. The wind speed. Why don't you take a minute to read that on your own? But we get all these here's the scenario that we get. Okay, we have a mu of 8. That's what we think is true. That's our null hypothesis. Our alternative hypothesis is that it's not equal to 8. I can easily calculate the z value. He didn't write down the formula here, but you can calculate what the the test value is. I come up with 1.89. So now that I have the 18.9, I want to calculate what the area is under the curve. So remember, area under the curve on a z table is to the left. So for 18.9, the amount of area to the left is 0.9706. Okay, well that's fine. So if it's 0.9706, subtract that from 1, that gives me 0.0294. So what I'm saying is that there's 2.9%, roughly speaking, 2.9% is to the right. There it is right there. 2.94% is to the right of that number. Okay, so it's 2.9% is to the right of that number that we have, the 8.2. Okay, the 8.2 is the average wind speed, 8.2 that's my X bar. Okay, to the right is 2.9%. I wish we'd stay with one or the other. I wish we'd just stick with percentages, but unfortunately we don't. Okay, but it's a two-tailed test. What we're saying here in the null hypothesis, the alternative hypothesis, is that it's not equal to 8. So we have to worry about this area and this area. So it'd be very legitimate for you to say, well, why would I do a two-tailed test? My X bar came back bigger than my mu. That's just to maintain the integrity of the test is what it boils down to, okay? So if it's a two-tailed test, by golly, you got to stick to that, even though you come up with a number that kind of militates as force and effect against. It militates against the two-tailed test. You still got to do it this way. So you have an area here, this area plus this area, add them up, you double it up. So now you have a total probability 0.0588. So there's a 0.0588 probability that you'll be one side or the other. You'll be at 8.2 or more extreme. This one's a little bit awkward, I admit, but that's just the way that they like to do it. Okay, so now you say, okay, I'm going to reject the claim because there's a 5.88% chance that I could be wrong just by random chance, and I just told you that my alpha is 0.05, so that's why I reject it.